to do part 11 and part 12, I was looking for my little sheet that had that has the equations on it. But anyway, and he said that this Henry's Law, part 12, and he's right, that actually that one is pretty darn straightforward. He said it's right up there with freezing point pressure, boiling point elevation. So we talk about solubility, and it might be a little bit different than you think. But solubility just means how much solute you can shove in a certain amount of solvent, or how concentrated your solution can be before that solvent stops taking any more solute. Okay, there's a limit to solubility usually. And actually, instead of, let's see, I'll play this one. I can't remember what this video does. Highly soluble, moderately soluble, slightly soluble, sparingly soluble, or insoluble. And actually, you will see these terms, and this is for the most solute would dissolve for a given amount of solvent or solution, and this is the least amount of solute would dissolve. What I started to say is sometimes you'll hear either non-quantitative terms or just general terms. You'll hear these thrown out. Saturated solution means, and again, I kind of mentioned sludge. If you see the sludge at the bottom of the solution, you know that you have saturated it with that solute. Okay. I'll kind of talk about the cool little equilibrium that goes on between the sludge and the solution coming up. Unsaturated solution means that you could just go ahead and dissolve more in. So yeah, this is just water, and this is water from my fertilizer here. It does make that slick. Oh well. So yeah, this would be my solute. This is my solvent in the solution. Okay, so as long as I can go ahead and mix it and get no sludge, that means it's unsaturated. Wow. Unsaturated. Supersaturated, actually, I've got a prop for that coming up, but supersaturated means that you have anything super in front of it means it's unstable. So supersaturated means that you have actually shoved a certain amount of solute, in this case, into the solvent, into the solution, and it's beyond the saturation amount. It's over 100% saturated. Okay? So I don't think I'm going to show you these. I'm just going to go right to the supersaturated. What does that look like? We have, and we've done this before. We're from left to right. You kind of have time going on. So freshly, that looks like a pile of poo, but it's not. So freshly, if we put your solute in the bottom of your beaker, you're going to freshly we have that dissolving process. From left to right, now we have the dissolving process, which those pink arrows are dissolving, and then those black arrows are the precipitating. So it's a dynamic. We'll be talking more about dynamic things. It's like it's not steady. Some go up, some come down, but not at equilibrium yet. Notice this last one. It's quite clever. They even changed the color. To me, the third beaker looks more pink or tan or whatever than So if you get a little bit of time, hopefully you would tell me that the length of these arrows are the same to extent of dissolving as the precipitating. So again, it's dynamic. And if they're the same rate, which is what those arrows are trying to show you, it's in what we say equilibrium. And this one was actually what I gave you, kind of application of supersaturated saturated solution. All right. Now usually, see this all a little bit of time. Oh no, it didn't. Just got some sludge there. So pink and saturated. Oh, it's like if I was patient enough, it could have started all the way. But just off the top of your head, if I want to get, what do I do to make candy to get that sugar involved? Not evaporated, because that's going the wrong direction by evaporating water. For candy, you're making it before?
No.
No?
Or wait, maybe Nino's like the sticks. They got the sugar twisted.
Yes. Yeah. So I was going to say heat. So I put it on the stove and heat it up. Okay, in the case of sugar, actually, if I increase the temperature, it increases its solubility. Okay, so we have this temperature effect on will a solute dissolve more or less in the solvent, the effective temperature. But it's not that straightforward. I wish it were. So we know we can write chemical equations from left to right, and actually I'm going to kind of show you the process here from left to right. If we start as separate solid and a solid solute, this is solid solutes and solvent. We're going to mix them together and we're going to make a solution. So that is your solute and solvent. Oh, two-way arrow. Well, we'll definitely be talking more about this. This is what we call not a one-way sort of situation, but it's a two-way situation. What we saw in the middle of the last beaker a few slides ago. Okay, we saw some of the solution breaking back down, precipitating out back into the sludge at the bottom and the solvent, and some of it was going ahead and dissolving again. Okay, notice this is again what that third beaker showed. So, what about temperature? Well, here in a minute we're going to kind of talk about if we put it on the stove, we are adding heat, and we're going to actually see heat is on the reactant side if you put it on the stove. If we're cooling it down, we're actually removing heat, and actually we're going to actually put heat on the product side, keeping the heat off. So here we go. Sugar's not up here, but we have some other things up here. What this graph is showing you is solubility along the y-axis and temperature along the x-axis. So if we pick any curve, like we could pick this for, let's pick a steep one. Potassium nitrate. Check this out. So this is potassium nitrate. As we increase the temperature, what happens to solubility? It increases, it goes up. So if you have a steep curve like potassium nitrate, that means that it has a great drastic change, right? Well, we talked a little bit about slope direction. So would you call this a positive slope or a negative slope? I would call it a positive slope. If you have a positive slope, that means as you increase the temperature, you're going to increase the solubility. Well, check out, is it cerium-2 sulfates? Wait, cerium-6. Voltage charge. Sorry, cerium-3, final answer. Cerium-3 sulfate. I'm thinking negative slope for this guy. So what happens to solubility as I increase the temperature? It decreases. Yeah. So there are some, and you don't put them on a stove. You put them on a stove, solubility is going to, you heat them up, solubility is going to decrease. Oh, by the way, units over here, and you might need this for homework and stuff. Solubility, you can express it in different ways. This is kind of a common way. Grams of the solute per 100 grams of the solvent. Not the solution, the solvent, water. Okay? So make sure you look closely at your units there. Okay, so this is just a, this is in room temperature. We see this ammonium chloride. It's dissolved in water. Let's see, let's go back, find ammonium chloride. Let's see it on here. Oh, there's sugar. Anyway, so go ahead and cool it down. And check this out. We get sludge. So would you say in the colder temperature, is it more soluble or less soluble? Less soluble. And the fact that we had no sludge here, I don't even know if this was saturated. But I know as I cooled it down, at some point I reached the saturation and it began to go ahead and precipitate out.
So that doesn't happen when you're like, so if you're making tea and you put a whole bunch of sugar in there when it's warm, it goes into it, but if you make it cold, then it doesn't. Right?
Well, depending on depending on if our T, it would go to the bottom if we cool it down below the saturation. If we cooled it down and the amount that was dissolved could no longer be dissolved. So it could potentially get that. But if you never see any sludge after you cool down, it just means that when you added your sugar, you didn't add a whole lot. Yeah,
because like some drinks you have to like shake well before opening. It's like the temperature decreases and that's
okay. Yeah. Because you cooled it down and it's formed a layer. Yeah. Cool. So let's take a look at this video real quick. The compound, there is definitely energy tied up in when those the cation and anion are in their crystalline structure. So we have to break it, and then energy is released as bonds are formed between the water molecules and now the cation and anion. So I have a lot to add to this. Endothermic, exothermic. So if it's positive, that's endothermic. That's breaking of those bonds. If it's negative, like this, that means it's exothermic, forming bonds. These two are the waters of hydration surrounding the cation and anion. So these are some enthalpies of formation of various ions. I don't have a whole lot to add. I don't think you have any problems like this. Okay, so that's kind of a little blah blah. This is not blah blah. Okay, so Le Chatelier's principle, I'm going to introduce it in Unit 1 right now. Unit 2, we're going to talk about reaction kinetics, how fast a reaction occurs. It's going to be kind of fun. Unit 3, we're going to get back to chemical equilibrium. So in Unit 3 and Unit 1, I'm going to introduce the Chatelier's principle, and it's going to reappear in Unit 3 is my point. So the Chatelier's principle, it's kind of oh, that makes sense. The Chatelier's principle says that if you take a system that's minding its own business in chemical equilibrium, the equilibrium we looked at a minute ago was this one. If you see a two-way arrow, you know that's equilibrium. Equilibrium is going on. What we talked about was we had the solid solute plus the solvent in equilibrium with the solution. Okay. So according to Le Chatelier's principle, and it applies to more than just this, it says if you stress a system that's in equilibrium, just like all of us, something's going to happen as a result of that stress. That's Le Chatelier's principle. What happens depends upon the stress. So how could you stress a system? Well, these are all ways that you could take a system at equilibrium and you could wake it up. You could go ahead and change the concentration of a reactant or product. So, we could change the temperature. We could change the pressure. Pressure is more for, like, if you have a system in equilibrium that has gases. So let's go back to kind of the question at hand, where we're dissolving a solid solute in a solvent to make a solution. Well, the effect of changing the temperature on the equilibrium will depend on whether this equilibrium generates energy, is exothermic, or it requires energy, it's endothermic. Okay, I don't know if you caught that, but what I did just a minute ago is this my equilibrium? If it's exothermic, energy. If it's endothermic, energy. Okay, so it makes a difference. So let's see what that looks like. So if we go with dissolving process, that is endothermic. Okay, that means our delta H of our enthalpy of dissolving is positive. Okay, heat's going to be a reactant, so it looks like this. this would be for most substances. Most substances are endothermic to dissolve them. I guess we're all a little stressed out, but why do we need that door open to that equipment room? And it goes off and off. Okay, this is only one of two possibilities, endothermic. So, Le Chatelier's principle in action now. It's kind of like a push or a pull. Le Chatelier's principle is totally like a push or a pull. So if we add heat, do you see where this is going to be like a push? I'm going to go over here and I'm going to push. Le Chatelier's principle. What does that mean? It means that I'm going to have more of my solution formed. What is my solution? That's actually dissolved solid, okay? So if I stress the system, it's at equilibrium, mind its own business, by adding more heat, okay, it's not going to be at equilibrium anymore. So this, it's going to establish what we say a new equilibrium, a new day, where the quantities on either side of the equilibrium area are going to be different. So in this case, with my push, I'm going to have more solution. So this is going to be more over here. And I don't necessarily need to put less over here because I just need to, to me, when I think about trying to reestablish a new equilibrium, I've got endless amounts of solvents I can dissolve. So I'm just going to have more solid dissolved. So that's Le Chatelier's principle. In that case, we have a push.
So that's why when you increase temperature of a solvent, it makes it more soluble.
Right.
Okay. Because of the equilibrium.
Yes, exactly. That's how I sugar. That's why if I wanted this to go, if I wanted more and more to go in solution, I would heat it up.
Okay.
Handy. But you remember a little bit ago, we looked at that graph, and most of them had a positive slope, and that like cerium 2 sulfate had a negative slope. Okay, see, that's going to be just the opposite. Okay, when I heat it up, I'm going to have less of the solution. So, the Le Chatelier principle is a general principle, applies to all chemical equilibrium, and this different stresses. Yeah, in this case, the heat. But that only happens if it's an endothermic process to dissolve it in the first place. Yep, so solubility of a solute will increase with increasing temperature if you're talking about an endothermic equilibrium like that. So let's switch it up a little bit. And to me, the only one I think I saw on the list of different salts that we saw, the solubility of salts, would be the cerium 2 sulfate. Okay? So let's look at something that releases energy, is exothermic. So on the next slide, you're going to see me put energy or heat on the product side. Okay, exothermic. So now in my tug of war, I'm actually going to go on my product side and I'm going to push if I'm adding heat. Okay, so if I add heat, I'm going to stress the system. It's going to form a new reality. It's going to get a new equilibrium. Okay, so it's going to, I think of it as a push. This is kind of talking about a pull, but it's going to actually push the equilibrium over from what we say, the product side to the reactant side. And what is the reactant? It's that sludge. Okay, so it will go back to the reactant side, and what is, like I said, what's the reactant side? It's going to precipitate more. So in this case, with the cerium sulfate, if I was heating up on the stove, I would see more and more come out of solution. Trapped. Okay.
So if the stressor is like pressure?
Yeah, that would let me do it for you. She asked if the stressor is pressure. And to me, pressure comes into account if our reactants are products of gases. Yep. You got it. Okay, so in this case, if it's an exothermic, we put heat on the product side, we heat it up, then if you add more heat, it's gonna push it over there. Okay. Le Chatelier's principle. So hold that thought. More Le Chatelier is coming. Well, I kind of finish up this part talking about changing the solute from a solid to a gas. Okay, like soda pop. You know, soda pop is got carbon dioxide that makes it so fizzy. Sugar water. So, like this says, in general, if your solute is a gas, this whole process is usually exothermic. So this process is exothermic. So as you heat it up, what do you think? Do you get more dissolved in solution, more gas dissolved in solution, or as you heat it up, do you get the gas to come out of the solvent? How many people think it's the first one? If you heat it up, you get more gas to go into your solution. Yep. So I'm going to go ahead and end it here. So if this is a gas, this says it's exothermic. So I'm going to heat it up, and your two options are: if I heat it up, and I'm not going to get more gas dissolved, or if I heat it up, am I going to get more gas out? So how many people think I'm going to get more gas dissolved? How many people think I get more gas out? I do too. One of the things, so like as geeky as it is or whatever, like if you get some cold tap water, so water has gas dissolved in it. But you get cold tap water, and you go ahead and let it sit out room temperature and come back, sometimes you'll see little bubbles coming on the inside. So it was aerated or whatever it had. Then, or just air. And it comes out of solution and it gets warmer. It has all sorts of consequences with regard to carbonated beverages too. But that's generally how any gas solute would behave in a liquid salt.
Because like after a while, like carbonated beverages are not that much fun.
Yeah, and kind of like that. Yeah, and if you have a carbonated beverage, you want to, and you pop the top, you want your odds at keeping the CO2 in solution are better if you refrigerate it versus if you let it out. Yep. So the addition of heat will make the solubility of the gas go down, which means, you'll have gas coming out.
One time I put a bottle of pop in a jacuzzi for like a really long time as an experiment, and it like popped, well it got bigger, the bottle kind of busted, and then he opened it and
There's no phases left or
no, because it was hot and like all the gas had gotten out of it. Whoa, that makes sense.
So if we were to cool it, now keep it, and this is a general Le Chatelier's principle thing. If you remove something, you pull. So to me, it's if you add something, you push. If you remove something, you pull. So if I go over here and I cool it down, okay, my equilibrium is going to come this way. I actually go on the side of the equation and I either pull if I'm removing or push if I'm adding. So if we cool it down, more is going to dissolve. Yeah. So solubility of most gases in a liquid will decrease as it gets warmer. Right, so here we go. A bunch of negative slopes. Okay. Again, we have temperature along the x-axis and solubility along the y-axis. The units of solubility are different. They're units of moles of gas per liter. Right. So, and this is kind of what we talked about, showing you, this is just a glass, yeah, exactly. Small bubbles in the glass of the chilled water form when the water warms to room temperature. Solubility is decreased because because of the warmer temperature. Fish kill. So with warmer waters in the summertime, so warm waters, you have less air, including oxygen, dissolved in your little fishies to use. So this is showing you picking out one particular gas, oxygen, and it's showing you its solubility at various temperatures. So as we get warmer, this is the solubility going down, and this is parts per million O2. All right. Okay. Extra credit. I posted up there. So let's take a look at Henry's Law. All right. I tried to play this movie. I looked for this movie, I promise. Oh, goodness gracious. I'll try it one more time. No, it's not going to go. Silly thing. Well, what happens when you open a can? It pops. Exactly. In order to kind of set the stage, and I think that's what this video would say. Oh, I'll tell you the video. Here is my can. Not a beaker anymore, it's a can. Okay, and at the factory, here's my liquid, my sugar water, and of course I have carbon dioxide, those are my carbon dioxide particles. And it's all sealed up before we open it. And I'm going to go ahead and put carbon dioxide particles here too. So it's pressurized. So sometimes you hear the whooshing. So that's the carbon dioxide coming out. Now what Henry's Law says in a nutshell, and we'll kind of quantitate it, is that if you, how do I say this? If it's nice and pressurized without opening it, there's this sort of understanding that the amount of gas particles I can have dissolved here is a function of the pressure of gas I have in the liquid above it. So, we'll kind of confer this with Henry's Law. As I open it, these gas particles, these are my carbon dioxide, go away. Now granted, now I have nitrogen and oxygen in the room that kind of come here. But since these are gone, that means that it's fair game. These guys no longer, and I'll kind of show you this in Henry's Law, these guys are like, I'm out of here. I don't have my carbon dioxide in my headspace anymore. So Henry's Law basically says is a function of how soluble can you get your gas if you have it pressurized over the liquid like this. It's a solubility of gas in the liquid relative to the pressure you have over the liquid. Okay? So this is kind of showing you, of course, those three atoms, those are carbon dioxide gas molecules, and they're kind of leaving. And again, why would they leave compared to when they were in their bottle? When they're in picture anything, like a 2-liter bottle, that little neck up there, I was just picture little CO2 particles. It's pressurized with carbon dioxide. So once you take carbon dioxide gone, they're all going to work their way eventually out of it. It goes flat. Okay? This is trying to kind of show you, we have kind of we've done this before, we have a movable platform where I have 1 weight there, 2 weights there, 3 weights there. So the weights do a few things. One of the things that the weight does is to take those gas particles that are in blue and increase the pressure. Okay? And can you see where as I increase the pressure from left to right of the gas particles that are hovering over that liquid that I'm trying to dissolve gas particles in, as I increase the pressure of the gas particles, well, what happens is solubility. That's Henry's Law. You have a bluer solution over here because it's got the highest gas pressure. Okay, over here, not so blue, has a lower gas pressure. In the headspace above it, that's Henry's Law. So we're kind of talking about gas here in headspace and gas here in the liquid. It's kind of cool. It makes sense. I'm like, oh, that's cool. So this should be, and again, I was trying to find my sheet that you guys are I'm going to hand out tomorrow. But your sheet, your equation sheet should have this on it too. Does anybody have the equation sheet with them? I don't. This is Henry's Law. where C stands for the concentration of the gas that's dissolved. Benny's got it. Do you have it?
Somewhere. Yeah.
Good. I was just gonna. Yay! Yep, that's the last one we didn't know yet. Yep, where C of the gas is the concentration of the gas, the solubility of the gas that's dissolved in the solvent. Now KH is Henry's law constant, so it'll be specific for, I'm pretty sure that it's specific for the gas and the solute and the temperature. It's a very nitpicky constant. And sub H means Henry, so Henry's constant, Henry's law constant. And the P of the gas was what I've been talking about. That's up here. That's the partial pressure of the gas in the headspace above the liquid where you're trying to dissolve gas. Okay? So as we increase the pressure of the gas, we increase the concentration of the gas as it dissolves in the liquid solvent. That's it. So a common unit of solubility of the gas would be moles of gas per liter of solution. Good units of the partial pressure of the gas in the headspace over the solution would be either units of millimeters of mercury or atmospheres. And then whatever units the concentration and pressure of the gas are, kind of set the units for Henry's law constant. But remember, I hate these 3 slash things. We'll see in a minute what that looks like. So KH, I said, is very nitpicky. It depends upon what you're trying to dissolve, which gas you're trying to dissolve, what you're dissolving it in, it's usually water, but not necessarily the solvent, and the temperature at which this whole dissolving process occurs. Very picky, very picky. So here we have, these are dissolving these gases in water at 25 degrees Celsius. And notice the big M, what does the big M stand for? Molarity, yeah, that's molarity. Molarity of gas dissolving in the solvent per millimeter of mercury of the pressure, the gas in the headspace above it. All right, so let's do a problem. So if I was going to draw a picture of this, here's my mountains. Kind of irrelevant, but here is my lake. Okay. So we have some information here. It's given that altitude. We don't care about that, but it says the partial pressure of my oxygen above this lake. Here's my oxygen particles, and the partial pressure of my oxygen is 0.14 atmospheres. And it says what amount of oxygen in parts per million can I dissolve? So question mark. Concentration of O2 in parts per million. We're going to have to remember what parts per million are. How much can we dissolve in this lake, given that Henry's law constant, case of H, is 1.66 times 10 to the 9-6. That's moles per liter per millimeters of mercury. Knowing Henry's law constant says this. Doesn't look too bad. Okay, so Henry's law constant times partial pressure. Okay, what's going to be interesting is to try to get the oxygen from units of moles per liter to units of parts per million. So we just kind of plug and chug. The solubility of the gas, in order to use the Henry's law constant that was given, that's a tricky one. We have to get, since it's given in units of millimeters of mercury, we have to get from atmospheres to millimeters of mercury. I did not give you this one, did I? Sorry. Let's think of it. Jot that down. And that's one thing, hopefully you know by now. 1 atmosphere is equal to 760 millimeters of mercury exactly. So that's going to be my pressure I plug in up here. Then I can go ahead and apply Henry's law. Oops, sorry, if I get that. Apply Henry's law, and it looks like this, where I just kind of put Henry's law constant in brackets because it's got kind of this strange sort of thing. Henry's law constant, which says 1.66 times 10 to the minus 6. Units are molarity per millimeters mercury. Molarity is moles of O2 per liter of solution, and also in the denominator I have millimeters mercury. And we said that units of millimeters mercury, our partial pressure of oxygen is 1.1 times 10 to the minus second. So go ahead and let units cancel and round to 2 sig figs, and you end up with the solubility 1.8 times 10 to the minus fourth, and units would be moles of O2 per liter of solution. And this is where we have to remember that, I don't know if one of these are on the test, I don't think so. You have to remember that if it's dilute, like not very concentrated, and the solvent is water, dilute aqueous, that's the same thing as milligrams per liter. So, can we get to milligrams per liter from moles per liter? Yep, we're going to have to use the molar mass of an O2 molecule. What is it? It's not 16, it's 32, yep. So our next term, if we go ahead and make it 32 grams O2 over 1 mole of O2. And then we need to get to milligrams. So how do we get to milligrams from grams? Yep. 1,000 milligrams over 1 gram. Yep. So round to 2 sig figs, you're looking at 5.7 milligrams of O2 per liter of solution, which is approximately to 5.7 parts per million. Okay, so that's one type of problem. You could run into this sort of problem. Looks like this. Let's do one more. Okay, so solubility of water is 0 degrees. Okay, so we have 2 scenarios. The way I would work this is I would kind of, in my sketch, kind of divide it into my 2 scenarios. Over here, and the temperature for both is 0 degrees Celsius if you read it a few times. And if you have the partial pressure of nitrogen, 0.790 atmospheres, the solubility is, concentration of N2 is 8.21 times 10 to the negative fourth moles per liter. And if you jack up the, if you jack up the pressure, what's going to happen to the solubility? I think increase, yep. So we're supposed to come up with this. So we can do it a couple different ways. What I'm going to do, see me do on the slides, is actually I'm going to use these 2 to come up with Henry's law constant. And then once I have Henry's law constant, go ahead and use it. Okay, just remember that according to Henry's law, we have this relationship between our nitrogen gas that dissolves, partial pressure of the nitrogen gas, and Henry's law constant. So if we rearrange Henry's law, we can get Henry's law constant will just simply be the solubility of the gas divided by the partial pressure of the gas and the head speed over it. So here we go. Henry's law constant, and again, we can only do this because it's a constant temperature, will be that 0.00821 moles per liter, which is the same thing as 8.21 times 10 to the minus 4th moles per liter, divided by 0.790 atmospheres, round to 3 sig figs, and you're looking at a constant of 0.00104, and units would be moles per liter, and also in the denominator, units of atmospheres. We're almost done. So we take that one, plug it into Henry's law. So the new concentration of the nitrogen gas would be the constant, 0.00104 moles per liter per atmosphere, times the new partial pressure of nitrogen, round to 3 sig figs again. You're looking at a solubility of there's too many zeros and fours and ones here. The new concentration would be higher, 0.00114 moles per liter. Dun, 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 dun. So tomorrow's test, over across the way, I've got a lab before y'all's test at 10, but sometimes it doesn't take the full time. But I'll be on campus by 9, and then lab at 10, and then test. It's going to be 502 this semester. Okay. Yeah, but just right across the hall. Mm-hmm. Yep. Okay. Good stuff, Maynard. What doesn't kill us makes us stronger.